Hello again out there in remote learning land. We're going to chat a little more about igneous rocks today, a little more about their differences, right? Trying to really get to the bottom of all this. So let's get cranking. How do these two igneous rocks differ? If you remember from the other day, take a minute, think about it. Okay, obviously there's a coloration difference there. And you can see this is much lighter, that's much darker. Maybe you remember the terms felsic and mafic. How else do they differ? Well, clearly they have different size crystals, right? You can see this has much bigger crystals, this much smaller, which means this one must have cooled a lot slower, and this one, of course, much faster. Well, how else do they differ? You could say, oh, by texture, right? Because bigger crystals means a coarser texture. And smaller crystals means a finer texture. So you can say a lot of things here about the differences between these two rocks. What do they have in common? They were both born from molten material, just that this one, of course, exited the earth, right? Cooled faster, and this one stayed in the earth, cooled much slower. All right? So texture is all about the size of the crystal, and the bigger the crystals, the coarser it is, right? These are all coarse samples, because they have big crystals, because they cooled slowly beneath the surface intrusively. Okay? Over here, these are small crystals and then no crystals. Well, these all cooled at the surface, and as you go to the right here, it cooled even faster and faster. Okay? Those are all the extrusive examples there. Okay? How does the texture of these two intrusive rocks differ? Well, they're both intrusive now, but clearly you can see these crystals are a lot bigger than these. Okay, which means the one on the right there must have cooled a lot slower, right? The slower the cooling, the bigger the crystals. The longer a lady is pregnant, for example, right, the bigger her belly gets. Well, same type of thing here. The longer the rock cools, the bigger the crystals get. So this would be considered coarse, and this very coarse. Okay? And that's what's going on with this chart. So on the left side, we have coarse examples. You can see there, big crystals. All right? The magma cooled slowly. They have a lot of time to grow, could be hundreds to thousands of years. And you'll have those interlocking crystals. And the examples, of course, would be granite and gabbro. On the right side, however, it cooled even slower, right? And it took even longer. And now you have these monster crystals, could have been thousands to millions of years cooling. And an example would be a pegmatite. And you'll find those on your chart. You won't find a name for a dark rock there with monster crystals because of the mineral arrangements. You generally don't find that. But you will find the felsic rock with big crystals there. Okay. And then, of course, how do extrusive textures differ? These are both extrusive textures, but clearly not the same, right? Which one cooled faster? Which one cooled slower? Well, if you're saying that this one cooled faster, you're right? Gas escaped. This one shot out of a volcano. Whereas this one cooled either just at the surface, maybe a little below, has potential for little crystals there, because it cooled a little slower than that one, but both are still considered extrusive. Okay? So here are your extrusive textures. These are called fine-grained. You don't really see the gas pockets, and you might see some speckles of minerals in there. Okay? Fast-cooling lava, right, at the surface. Crystals grow, in very little time, so they're just very small, and your examples would be basalt and rhyolite. We talked yesterday about this being most of the ocean floor and the surface of the moon. Rhyolite, you'll find more on the continents. Okay. However, if it cools really fast, you'll get those vesicular textures, those gas pockets, right? That was that pumice stone we talked about, that callus scraper. And again, the holes come from rapidly escaping gases, and they leave the vesicular texture, vesicles. Okay. And that's what's going on here. One of a classic movie, not sure if you ever saw it a while back, Shawshank Redemption. Morgan Freeman is trying to meet up with a buddy of his, and his buddy hides something for him under what he describes as this piece of large black volcanic glass. So hopefully you're thinking a beautiful chunk of obsidian. And he says it's a rock that has no business being in a main hayfield. What he's talking about there is, middle of a hayfield, there is no volcano. So why would there be a volcanic rock there? And that was the whole idea. He put something that didn't belong there so that Morgan Freeman could identify as this is out of place. And that's where he hid something underneath for him. I'll play you just a little clip from it. But you'd have to see the whole movie to get the full context. There it is, a little dirty, but you can see it's a much darker rock. If it were cleaned off, it would shine like that gorgeous volcanic glass, right? That obsidian. All right, and that clearly doesn't belong in the middle of a hayfield in Maine. There's no volcanoes there. If you cleaned it off, that's what it would look like, that beautiful obsidian. When you see it like that, they call that snowflake obsidian, right? It's got little impurities mixed in, but it's that black volcanic glass. And there it is, your glassy texture, non-crystalline, no crystals there, right? It cooled too quickly. Absolutely extrusive, right? Volcanic. And the crystals just don't have time to grow. Okay? Obsidian usually appears black, but strangely, of course, it's still considered a felsic rock. It's one of those strange ones because it has low-density minerals in it. A lot of silicon and aluminum, and it doesn't fit into the mafic category because it doesn't have iron, it doesn't have magnesium. It's not made of those denser materials. So the coloration, remember, like quartz, can come in many colors, right? All you need is a little impurity in there. You can get any color you want. But the matrix of it, the full part of it, are all those felsic minerals. Okay? What does this graph look like? Well, let's see if you can figure that out. Time versus crystal size. Hit pause, see if you can figure it out. Hopefully you realize the more time you let it to cool, the bigger the crystal size are going to grow there. And that's what's going on there. Okay, as time increases, crystal size also increases. Okay, this is showing you, again, bigger crystals as you have more time to cool. Okay? Okay. How about this one here? Rate versus crystal size. Now remember, time and rate are a little different, right? Rate at which you do something versus the time it took you to do something. Well, if you increase the rate, that means you did it faster. You did it in less time. So there you go. If you increase the rate, well, then you have to decrease your crystal size because you had less time to form. Okay? Okay. We'll go through these with you real quick, see if you can figure out these textures. Hit pause, see if you can figure them out. And here we go. All right, so you have kind of a gas pockety thing going on here, right? Vesicular. Here you have that glassy texture. Here you have some pretty big crystals. So there's your vesicular. Hopefully you spotted that one right away. And then, of course, the big crystals is a coarse texture. And these would be much smaller crystals for a fine texture. And then, of course, there's your glassy texture. For something with a very coarse texture, you would need bigger crystals than that, right? That pegmatite, where the crystals are enormous. Okay? So hopefully you did all right on that. Some extra summary questions there for you. All right, take your time, crank those out, and we'll chat about it in a minute. See you there.